Well, about to get underway on BBC1, another miscellany of lunchtime guests at Pebble Mill. And they include the endearing Arthur Marshall, who evokes some bittersweet memories of school days. Also, Michael Smith, who concludes his new English cookery course with roly-poly pudding. And that's on BBC1. This is BBC2, however, and we look at some more of the common difficulties encountered when studying maths.
Problem. Demonstrate that the exterior angles of a convex polygon add up to 360 degrees.
How do you feel about that? Not too happy, I expect. And part of the problem is a language problem. If you don't know what polygon means, if you don't know what convex means, and if you don't know what exterior angles mean, you can't even begin. So let's look at those words one at a time. A polygon is a shape with straight sides, like this. Or this, or this. That last one, though, is not convex because its sides dent in towards the centre, here. So that one's no good. The exterior angles of a convex polygon are these. Now we can see what the statement is saying. It's saying that this lot add up to 360 degrees. And so do this lot. And so did this lot. Got it? Take it easy. Just take in what's claimed. Firstly, did it look at all likely? No? Well, nor did it to me. But I happen to know it is so. So don't panic. Step back to something that you do know. Are you confident about angles? One idea of angle is turn, and there are many everyday objects which work simply by turning. If I open this window, it does so by turning. When I come through this door, it turns and I turn it back. This is a very useful sort of turn. Many of you may have seen that. So that turning is an everyday experience which all of you have had and which all of you know about. What did I do then? I did a straight movement, and then I did a turning movement to get the handle where I wanted it. If I had wanted to put this somewhere else on the table, a straight movement and a turn, or back to where it started, a straight movement and a turn. Those two movements, translation and rotation, would have got that cup anywhere I wanted on the table, anywhere I wanted in the world. If I wanted to get to Mars, I can do it by a translation and a rotation. They are ideas, simple ideas, which have universal applications. That's the power and scope of mathematics. But how do we measure these two things? The first of them, translation, we measure simply in feet and inches. The ruler represents what we decided about that. We said that was a foot, and at some time man decided that a foot should be divided into 12 inches. It was a human decision. Turning is a bit more interesting. Watch this. When I get it there, it is back where I started. Indeed, if I did it several times, it would still be back where I started. The fact that it gets back where I started makes turning a particular sort of movement. And there's an inbuilt measurement of turn. That is, one complete turn. That inbuilt idea is mathematical. It's not a matter of human decision. Well, here we are back at the problem. We have a pentagon here with 5 angles, and the problem is, do they add up to 360 degrees? So, watch me. I'm a coffee cup. There's my handle, and I'm going to rotate and move forward, rotate and translate. We turn again, along, again, along, and here we are at the last one. Round we go, and here we are, back where I started. Now, if you watch that movement without the forward movements, just with the turn, what do we have? We have that, 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 and there we are. I made one complete turn. Convincing? Now, let's have a look at this angle. There is another way of looking at this, and that is as a sharp point with a sort of space between those two lines. That's a static idea of angle. Let's go round and collect them up. And there we are. We have all 5 of them. Let's see what they look like here. Fitting them together as we go round. Wait for it now. That one. And there we are. The last one fits in exactly. We have a complete circle. That's our complete turn. Now, I want to have another look at this angle. What time does this represent? That's right, 2 o'clock. And we didn't need any numbers to tell that, and it wouldn't have mattered whether that was a tiny wristwatch or the size of Big Ben. The static idea of angle corresponds with the idea of telling the time. Now, the dynamic idea of angle corresponds with duration of time. And if we look at this clock, if this hand here were to move through that, that would be a 10-minute interval. If this hand were to move through there, a 2-hour interval. They would have moved through the same angle, and that angle would have measured duration of time. Now, it is useful to us to have a smaller unit than a complete turn. And we could go about this in various ways. We could have decided to have 12 units in a complete turn, match it to the clock face, and match it to our feet and inches. But in fact, it so happens that the Babylonians thought there were 360 days in a year, and they divided a circle up into 360 parts, and we've always gone along with that. So if we take a clock face and we look at that, we can mark it out with 360 degrees round the edge. And that means that one of these divisions, the gap between 12 and 1, say, is in fact a 30-degree division. Now, we now see how angles link up with turn. They're just a purely arbitrary division of it. We'd already shown in our problem that we'd done a complete turn, and a complete turn happens to be 360 degrees because we agreed it was so. And in fact, that wraps up our problem. We have done what we set out to do. So, come the exam, we don't have all this fancy material. We don't want the examiner to carry home those heavy angles in his briefcase. So we're down to the usual tools of the trade, pen and paper. And if we look at the simplest polygon there is, that well-known shape, the triangle, then we see that we've got 3 big angles here that I need to turn through as I go through it. Are they going to add up to 360? Well, look at this corner here. Those 2 together certainly make up that halfway turn, and a halfway turn is 180. If I were to put in all of these and add the lot together, I'm going to have a halfway turn at each corner. I'm going to have 3 lots of 180 degrees. But I need to know something more. I need to know the angle sum of a triangle, but I do know it. It's 180 degrees. Those interior angles, the crosses, add up to 180 degrees. So they come to one lot of 180 degrees, and that leaves me, for the exterior angles, 2 lots of 180 degrees, 360 degrees, which is what we wanted. Now, that deals with a triangle. Let's now see if we can go on and deal with the pentagon. Here we have the pentagon. It's the same issue. There are interior angles which pair off with the exterior ones all the way round. And every time it comes to 180 degrees. So we have 5 lots of 180 degrees. What about the interior angles? What do we do about those? Well, we have a simple method. We chop the pentagon up into triangles. And we have 3 triangles, and each of those has 180 degrees in it. So if we take off 3 lots of 180 degrees, we are down again to the exterior angles. Lo and behold, 2 lots of 180 degrees, 360 again, and that deals with the pentagon. Now, that's taken a time to do what looks like one simple problem, but there's more to it than that. If we really got comfortable with angle, then that's going to make a great deal of difference to our understanding of geometry.